Hi, this is Sonia Doucette. In this video, I'll show you how to calculate the pH and the equilibrium concentrations for all species present for a solution of known molarity for a monoprotic acid. And this will be a case where we do not have to use the quadratic equation. The problem is calculate the pH and equilibrium concentrations of all species present in a 0.05 molar nitrous acid solution at 25 degrees Celsius. The first thing you want to do for this type of problem is to determine the species that are present initially and their acid-base properties. So in this case, the species initially present are nitrous acid and water. And their acid-base properties are that nitrous acid is an acid and that water can act as either an acid or a base. The next thing you want to do here is to write out the possible proton transfer reactions. And the reason you want to do this is because you need to find something called the principal reaction, which is the reaction that will head your ice table. Now the principal reaction is the reaction with the largest equilibrium constant, or K value. This means that it's the reaction that proceeds the furthest to the right or has relatively higher product concentrations. The reactions that are not the principal reactions are designated as the subsidiary reactions. I'm going to write the reactions first and then explain a little bit more about why we have to designate a principal reaction when I get to the part where we actually start to draw the ice table. So first, the proton transfer reactions. One is that you have nitrous acid transferring a proton to a water molecule to give you the hydronium ion plus the conjugate base of nitrous acid, which is the nitrite ion. And the Ka for this reaction is 4.5 times 10 to the negative 4. You can look that up in a table of acid dissociation constants. The next possible proton transfer reaction is where water transfers a proton to another water molecule. And again, this is because water can act as an acid or a base. When that happens, you're left with a hydronium ion, and this is the water molecule that has been transformed to an hydronium ion because it accepted a proton from the other water molecule, which donated its proton and is left over as just the hydroxide ion. And you know that this reaction has a special equilibrium constant designated as Kw, and that is 1.0 times 10 to the negative 14. So those are the two possible proton transfer reactions. And remember that I said the principal reaction will be the reaction with the greater equilibrium constant. So the reaction with the greater equilibrium constant is the first one, where nitrous acid donates a proton to the water molecule. So this will be the principal reaction, and then all other reactions, and there's just one in this case, are designated as the subsidiary reactions. So here's your subsidiary reaction. So the principal reaction, as I already mentioned, will be the reaction that heads the ice table. So let's draw the ice table. We have our principal reaction at the top. And then we have our three rows where I is the initial concentrations of all the species, C is the change in those concentrations as the reaction approaches equilibrium, and E is the concentration of those species at equilibrium. So we know from the problem that we're given the initial concentration of nitrous acid to be 0.05 molar. The concentration of hydronium ions is approximately 0. Only a very small amount is present initially. And then the initial concentration of the conjugate base nitrite is 0 to start because we're starting only with nitric acid. The change in those concentrations are going to be minus X for nitrous acid, and because for every 1 mole of nitrous acid lost, we gain 1 mole of hydronium ion and 1 mole of nitrite according to the reaction stoichiometry here. We're going to get plus X for hydronium ion and plus X for nitrite, the conjugate base. And now we can use these X values to write the equilibrium concentrations of each of the species present in terms of X. Nitrous acid will be 0.05 minus X, hydronium ion is X, and nitrite is also X. So now I want to talk a little bit more about why we need to choose a principal reaction. As you can see from the ICE table, we need to solve for X, which is the hydronium ion concentration, in order to find the pH and also to solve for the concentrations of all of the other species present. Once we know X, we can find the concentration of all of the other species present. But you can see by looking at the ICE table and also the 2 possible proton transfer reactions drawn previously, that hydronium ions can come from both proton transfer from nitrous acid to water and from proton transfer from one water molecule to another. So there are 2 sources of hydronium ions. If you solve for both hydronium ion concentrations, you'd also need to know the hydroxide ion concentration, which you don't know in this case. You'd need to be able to solve for this to find this hydronium ion concentration. However, you can ignore or neglect the hydronium ion concentration coming from proton transfer between the water molecules. So you can really ignore this hydronium ion concentration because it's so small compared to the hydronium ions that are coming from the principal reaction. And you can really see this by looking at the equilibrium expressions for the 2 proton transfer reactions. For the principal reaction, the equilibrium expression or equilibrium equation is Ka is equal to the hydronium ion concentration multiplied by the nitrite ion concentration divided by the nitrous acid concentration. And we know that this Ka value is equal to 4.5 times 10 to the negative 4. The equilibrium equation for the subsidiary reaction is Kw is equal to hydronium ion concentration times hydroxide ion concentration is equal to 1.0 times 10 to the negative 14. So the Ka for nitrous acid donating a proton to water is many, many orders of magnitude greater than the Kw describing the proton transfer from one water molecule to another. And that means that the number of hydronium ions from water dissociation that contribute to the total hydronium ion concentration is minuscule or very, very small compared to the number coming from the proton transfer from nitrous acid to water. And we can really see this if you write out the equilibrium constants for both of these proton transfer reaction in decimal form. So the Ka for the proton transfer from nitrous acid to water is 0.00045. The proton transfer between the two water molecules has an equilibrium value of 0.00000000000001. Let me see if I did that correctly. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 10 to the negative 14. In order to go out to that many decimal places for the Ka value for nitrous acid, we'd need to add 9 more zeros. 2, 3, 4, 5, 6, 7, 8, 9. So you can see that this value for the proton transfer between two water molecules is much, much smaller than the value for the proton transfer from nitrous acid to a water molecule to give you hydronium ions. So as a result of this, we can just ignore the hydronium ions coming from the water to water proton transfer, and as a result of that, we don't need to know the hydroxide ion concentration in order to solve for that hydronium ion concentration. So we neglect the hydronium ions coming from water and assume they only come from nitrous acid proton transfer. So the next thing we want to do is go back to the ICE table and write out this Ka expression for proton transfer from nitrous acid to water in terms of the equilibrium concentrations expressed using X. So we're going to write Ka is equal to X squared, because that is the concentration of hydronium ion times the concentration of the nitrite ion, divided by 0.05 minus X, which we've designated as the equilibrium concentration of nitrous acid. And we know that our Ka value is equal to 4.5 times 10 to the negative 4. We've looked that up in a table. Now this could be a messy equation to solve for X using. So what we can do is try to get rid of this X term. If we do that, things can get a lot easier. So what we do is make an assumption. We assume that 0.05 minus X is approximately equal to 0.05. So what we're really saying here is that X is so small that it will not change the initial nitrous acid concentration, which is 0.05, if we subtract X from it. So if we're going to assume this, we should test it first to make sure it's okay to make that assumption. So what we're going to do is rewrite this equation with the new assumption embedded in it. So now we have X squared over 0.05 is equal to 4.5 times 10 to the negative 4. What this gives us next is X squared, when we multiply both sides by 0.05, is equal to 2.25 times 10 to the negative 5. And then when we take the square root of that number, we find that X is equal to 0.00474. So to test the assumption, we now have to subtract that number from 0.05 and see if subtracting it makes a difference. So let's do that. We have 0.05 minus X. We found our X value when we make that assumption to be 0.00474. And if we make the subtraction, we get 0.0452. So because of what we're given in this problem, that the initial nitrous acid concentration is 0.05 molar, we only need to consider things to one significant figure, because that's what we're given for the problem. So if we consider one significant figure, we only consider this part, and what we end up with is 0.05, because we're rounding up from 4 to 5 because we have the 5 next to the 4. So for only one significant figure, we get 0.05 molar. And in this case, subtracting x from 0.05 does not change the number because we end up also with 0.05. So it's okay to make the assumption in this case. But let's say, just for the sake of argument, that we needed to round to two significant figures. So we had to go out to this many decimal places. In this case, when we subtract x from 0.05, we're left with 0.045. We wouldn't round up in this case. So this is the case of two significant figures. And in this case, subtracting x does change the initial nitrous acid concentration, and we would need to use the quadratic equation to solve here, and that can get really messy. So it's nice to make this assumption if we can, and in this case we are able to do that. So now all you need to do is go back to your ice table and solve for the concentrations of all species present. You know from your ice table that the concentration of the hydronium ion and also the concentration of nitrite is equal to x, and we've already solved for x here, and rounding that to the correct number of significant figures, we have a value of 0.005 molar for these two concentrations. Another species we need to solve for is nitrous acid, and we've already done that when we tested our assumption. So the concentration of nitrous acid we designated in our ice table as 0.05 minus x. We already know that subtracting x from that value does not change it. So at equilibrium we have 0.05 molar nitrous acid. Another species that needs to be solved for is the hydroxide ion concentration. We know that Kw is equal to the hydronium ion concentration times the hydroxide ion concentration. So using this relationship, we can solve for the hydroxide ion concentration by dividing Kw by the hydronium ion concentration, which we now know. So we just take 1.0 times 10 to the negative 14th. We divide by 0.00474, and I'm writing it all out instead of putting 0.005 because I don't want to round too early and make any rounding errors. And what you do when you solve and do the math here and round to the correct number of significant figures is you get 2 times 10 to the negative 2 molar. Negative 12 molar for your hydroxide ion concentration. The last thing you need to do is find the pH. And you already know a relationship that can help you do that. You know that pH is equal to the negative log of the hydronium ion concentration. So all you have to do is take the negative log of 0.00474, and again, not rounding too early to prevent rounding error. And when you do the math there, you get a pH of 2.3. So here are your answers. You have the concentration of all species present, which include your hydronium ion concentration, your nitrite ion, your nitrous acid concentration, your hydroxide ion concentration, and you're also asked to solve for the pH. So these are all of the concentrations you need to give when you're asked to solve this type of problem, and you also need to find the pH. And that's it. That's all you do.